Okay, so basically, a couple of points that are going to inform some of the rest of our discussion. I think everybody knows that electromagnetic waves travel at the speed of light. Um, Electromagnetic waves can all basically traverse whatever media through at some sort of frequency, and we know that over time, different frequencies have been chosen to support different communication types. So I'm going to talk a little bit about that. So basically, by policy and by um, characteristics, um, different electromagnetic waves are basically there's basically a frequency spectrum we're going to talk about, and that frequency spectrum is going to inform um, how we're going to use these different electromagnetic waves. Um, so we're going to get to that later on. So basically, the important thing to think about is this particular formula. So when you think about frequency and wavelength and speed of light in a vacuum, you have this following function. So because of this, um, if you know c, the speed of light, um, and you want to figure out, and you know either one of these two, you can always figure out the other value. So if you have any um, limitations on one or the other, you can always, you know, figure out the characteristics of an electromagnetic wave. So like I said, there's the electromagnetic spectrum. Um, for communication, um, this is a part of it that we are interested in. Um, so the frequencies from 10 to the 4 to 10 to the 16th, we're obviously not interested in anything below that. We're not interested in X-rays or gamma rays. Um, but as far as data communications, um, our copper twisted pair work with within these frequencies. Coax cable works within these frequencies. Our fiber optics are going to operate within this frequency spectrum, and satellite communications are going to operate within these frequency spectrums. So these are the spectrums that we're going to be focused on as far as network communication. So I want to start off with a bit of a discussion on communication satellites. We're going to talk about three different types: geostationary, medium Earth orbit, and low Earth orbit satellites. So in addition to using um, guided media um, and the next most popular media for network communication is the airwaves. We're going to talk about, the wireless and the phone networks later. In this particular lecture, we're going to talk a little bit about satellite communications. So basically, the three different types of satellites, like I said, you have the geostationary satellites. So at an altitude of about 35,000 kilometers, um, if a satellite at that altitude, orbits the Earth, basically it's going to basically follow the Earth's orbit. So it's going to look like it's not moving. That's why we call it geostationary. Obviously, at that distance, you have some serious latency of 270 milliseconds, and to get coverage around all over the Earth, all you would need is three satellites. Of course, there are a lot more than three geostationary satellites in space right now. You can't have any satellites in the upper or lower Van Allen belts because that's too dangerous. So in between the two, you have what you call your medium Earth orbit satellites. They obviously have a little bit less latency than the geostationary at 35 to 85 milliseconds, and you need about 10 of these to cover the entire Earth. And then below the lower Van Allen belt, at very very low kilometers. So we'll talk a little about what that number is. You have the low Earth orbiting satellites, and you need about 50. So there's two main low Earth orbiting satellite networks we're going to talk about. But this basically kind of gives you an overview of the different communication satellite types. So geostationary, so at above 35,000, well, I should say 35,000 kilometers, not feet. Unless the book, I'll have to take a look if the book is mixing that, because I thought the book said 35,000 feet, but the that chart does say 35,000 kilometers. Above 35,000 kilometers, satellites appear motionless in the skies because they're basically orbiting the Earth at the same speed the Earth is rotating. So you only need 3 satellites to cover the Earth, but there are many in use. So basically these days, each satellite has multiple antennas and transponders, so they have the ability to send multiple focused signals, so they can have a downward beam focused on a small geographical area, and spot beams, which are even smaller for a small coverage area. So say, for example, a satellite, a geostationary satellite that was focused on the United States could have one downward beam for the 48 states, and then a spot beam for Alaska and a spot beam for Hawaii. So the ITU has basically defined different frequency bands that are used by satellites. So these are all very heavily regulated. Each of these bands, you basically users have to share a time slot. So basically time division multiplexing is used, which we talked a little bit about in our previous lecture. We're going to talk about that a little bit more. So what you're going to find is that for the bandwidths that are these lower bandwidths, which have the advantage they're a little bit cheaper, there's not any real issues with the lower bandwidth as far as terrestrial interference or rain. So they work very well, but because they work very well and they're also cheaper, most of the satellite use is either on the L or the S band. So on the C band, you have to have you have to deal with terrestrial interference. So if you use the C band, you usually have to have receivers that are very high terrain, so you can mitigate against that. And if you're using these two bands, basically you have to have a backup links. So if one link has rain interference, you have a secondary link that you can use. But these are basically the principal satellite bands that are used for geostationary satellites. So basically, on the Earth you have to have receivers, and so there's been developed in recent years what's called VSATs, or very small aperture terminals. And the good thing about these is they're very low cost, and so they're very popular in rural areas and developing countries where that really depend on satellite communication. They don't have other infrastructures, and it's a lot cheaper um, to set up for satellite communication. So basically, they have small 1 meter antennas, and they have a 1 megabit per second uplink and several megabit per second downlink. They don't have enough power to um, directly communicate with each other, so they have to rely on some central hub to relay traffic between each other. But like I said, because they're low cost, um, they basically help, hard to get to areas, and developing countries have communication capability. They also have a longer round trip delay time, 540 milliseconds than your conventional terminals. So this next slide kind of shows you a setup. So in a particular area, you can have multiple VSATs, and they can communicate to a satellite, but they can't, they're sending data from one VSAT to another. You can't do that directly. So everything has to get sent to some centrally located hub, and that hub can, foster communication amongst the VSATs. Okay, next up we have what are called the medium Earth orbit satellites. So I'm talking about this basically for completion. They're not really used for data communications, but they're basically located in between the two Van Allen belts. They take about 6 hours to orbit the Earth, and they have to be tracked as they move through the sky. Pretty much the medium Earth orbiting satellites are used for navigation systems. So basically the common GPS, or global positioning system, uses medium Earth orbit satellites, so not really used for data communication. So basically, the next up you have the very low Earth orbiting satellites. In order for low Earth orbiting satellites to stay in orbit, their orbits are very quick. So basically, their rapid movement, and they cover a smaller area, so you need a large number to have a complete system that covers the Earth. The advantage of low Earth orbiting satellites is because they're close to the Earth, your ground stations don't need that much power, and your round trip latency is a lot better than the medium or the geostationary satellites. So basically, I'm going to talk a little bit about the two most popular low Earth orbiting satellite networks. One called Iridium, and another one called Globalstar. So the history of this isn't too important, but basically, at one time there was a plan to set up back in 1990, a network of 77 satellites. It got basically knocked down to 66. It took about 8 years to launch the Iridium network, but there wasn't a lot of interest in satellite phones. So the project went bankrupt, and all the satellites were rebought for pennies on the dollar, and then Iridium was relaunched in 2001. Basically, you have to use a special device to use the Iridium network. So you have a special device that you can make calls on. You can send data, do paging, faxing, and as well as get navigation information. So in a specialized device, the satellites are placed at an altitude of 750 kilometers in a circular polar orbit, and they arrange what's called the polar necklaces with one satellite for every 32 degrees of latitude. So they basically have a good coverage over the Earth, and each satellite has the ability to have 48 spot beams, and they can each support 3,840 channels. And basically the way it works in the Iridium network um, is, let's say you are a user on the North Pole and you want to talk to somebody in the South Pole, you're going to talk to the satellite closest to you, and the satellites basically communicate with each other until it gets to the user in the South Pole. This is compared to, just check. Okay, good. I put the drawings in there. Okay. This is in comparison to Globalstar. Now, Globalstar is a little bit smaller. It came after Iridium. It has a 48 satellite network. It has a much different switching scheme than Iridium. So in the Iridium network, like I said, the satellites do all the communications to get you to your end station. With Globalstar, the sender communicates with the satellite that's closest to it. And basically, Globalstar has multiple ground stations, and the ground stations communicate with each other to get you a communications path to the satellite near the receiver of the communication. The advantage of doing that, it puts the switching complexity on the ground rather than the satellite, so if something goes wrong, it's a lot easier to fix doing your switching in your ground stations. And since the ground stations can put out a powerful signal and receive a weak signal, lower power telephones can be used as opposed to Iridium, so you have to have a powerful and specialized receiver, because you're going to be communicating directly with a satellite that can only deal with strong signals since it's relatively far away. The ground station gives you more flexibility and the type of data receiver that you can use. So here we have a example of the Iridium network. So let's say you're over here, someplace in the, say, tip of South America, and you want to talk to somebody, and I assume that's probably Russia. You talk to this satellite, and it would set up a communication path to get you where you want to be, and then that receiver would receive the data from that satellite, and you would traverse across these satellites to get from one end to the other. And this is opposed to Globalstar, where if I had somebody here talking to somebody, from the North Pole talking to somebody in the South Pole, they send their communication to their closest satellite. The satellite beams that connection back down to the ground station. It goes through a ground station network to the last satellite available. Then the receiver receives it from the closest satellite. Okay, that's all I have to talk about regarding the satellite network. Next up, I want to talk about how do we send actual signals on our different transmission media. So I think now is a good time to take a quick break, and we'll come back to lecture 3.